Hello students, today we are going to discuss the new topic, characterization of the compounds by ultraviolet visible spectroscopy. Shortly we are going to call it as UV visible spectroscopy. A few days ago I attended a workshop on the characterization of the sample by spectroscopic methods. There we have discussed about UV spectroscopic method as well as the NMR technique. Later we are going to discuss about the NMR technique. Particularly in this video, we are going to discuss about UV visible spectroscopic methods. The spectroscopic methods, it has many advantages over the conventional methods. In this UV visible spectroscopy, the main application of this technique is to calculate the lambda maximum for the various conjugated compounds. It may be open chain compounds, or it may be aromatic compounds, or it may be alicyclic compounds. We discuss it in detail. The UV visible spectroscopy, the range of the UV radiation as well as visible radiation, it is about the 100 to 800 nanometer, 100 nanometer to 400 nanometer. We call it as UV range. Simultaneously, the 400 nanometer to 800 nanometer, we call it as visible range. Visible range means VIB or color is going to occur at this region, and UV region is further classified into two types. One is the vacuum UV. Vacuum UV means we are going to use the vacuum condition, because if oxygen is present or any other gaseous molecule is present, it is going to ionize that molecule. That's why we have to create the vacuum. And 200 nanometer to 400 nanometer, we call it as near UV region. Further, the Woodward-Fischer, they gave an empirical rules for the calculation of the lambda maximum for the compounds. So we can calculate the lambda maximum for the following compounds. First one is the open chain compounds. It may be conjugated dienes. And second one is the alicyclic compounds, means the cyclic compounds. And third one is the enones, that is alpha beta unsaturated carbonyl compounds. It is open chain carbonyl compounds, that is conjugated one. And the fourth one is the aromatic compounds. Aromatic compounds is comprises of benzene, naphthalene, anthracene, phenanthracene, like this. And the last one is the aromatic carbonyl compounds as well as the aromatic carboxylic compounds. It may comprises of the carbonyl compounds just like benzaldehyde, carboxylic compounds like benzoic acid, etc. For all these types of compounds, it is possible to calculate the lambda maximum by applying the Woodward-Fischer rules and some other rules. What are the basic conditions or basic values that we needed to calculate the lambda maximum? We discuss in Woodward gives the empirical rules for the calculation of the lambda maximum. He has taken a 1,3-butadiene as the basic core structure. To this core structure, we have to add the 217 nanometer, because this compound is going to observe at the 217 nanometer. For any alkyl substituent to this core structure is attached, we are going to consider it as a 1 alkyl substituent. To this we are going to add the 5 nanometer, and similarly if any ring is present or if any ring is attached to this core structure, we are going to consider this one as a ring residue. For this one also we have to add the 5 nanometer. And for the exocyclic double bond, exocyclic double bond means an 6-membered ring or a 5-membered ring when it is protruded a double bond to the outside. We are going to call this situation as exocyclic double bond. Okay, while discussing the problems, we can discuss in detail. For exocyclic double bond, we are going to add. Similarly, for the alicyclic compounds as well as polyenes, Woodward gives some empirical rules to calculate the lambda maximum. Basically, The alicyclic dienes, it is nothing but a 1,3-butadiene structure that is present in the cyclic ring. If the 1,3-butadiene present in the single ring or single 6-membered ring, we call the situation as homoannular. And if the 1,3-butadiene structure is present in the two rings, means each ring distributed with one double bond, we call the situation as heteroannular. Or shortly we can say, if the two double bonds are present in the same ring, we call the homoannular. To this we have to add 253 nanometer. If the heteroannular condition is there, we have to add the 214 nanometer. The rest of the rules is same as that of the conjugated dienes. For each alkyl substituent, you have to add the 5 nanometer. For ring residue, we have to add the 5 nanometer. For exocyclic double bond. Okay. So in this ring, in the homoannular ring, the double bond which is present at the junction of the two rings, we are going to consider it as exocyclic double bond. Similarly, in the heterocyclic ring also, at the junction of the two rings, there existence of one double bond. We are going to consider as one exocyclic double bond is present in this compound. For the extended conjugation means if any extra conjugation is there, apart from this homoannular and heteroannular, if any further double bond is present at the conjugation position. Conjugation position means after this a single bond and next double bond is there, we are going to consider it as one extended conjugation. For one extended conjugation, we have to add the 30 nanometer. Some cases, the both homoannular and heteroannular is present in the same compound. At that situation, we have to consider the homoannular because it is going to absorb at the higher nanometer, that is 253 nanometer. These are all the rules. By using these rules, let us calculate some of the compounds for their lambda maximum. So let us take the first example. In this case, this is the butadiene structure. We have to add the basic value 217 nanometer. To this, two alkyl substituents are there. Okay. These two are two alkyl substituents. For each alkyl substituent, we have to add the 5 nanometer. For two alkyl substituents, we have to add the plus 10 nanometer. Thus, on totaling, it is giving the value of 227 nanometer. Next compound is